Okay, so tonight we're going to go over 2.05b, and in the beginning we'll just do a quick review of 2.05, and then we'll move into the assignment for 2.05b, so at the end of the night you will have the assignment completed and you can just go ahead and submit that for full credit, and I'll explain more about that as we go through. All right, so let's get started. So the fundamental theorem of algebra is really important. It basically just tells us that the degree of the polynomial tells us the number of zeros or roots that the polynomial will have. And those roots can be real or they can be imaginary. So the kind of interesting thing about roots is that if they are real, they will show up as x-intercepts. If they are imaginary, they will not show up as x-intercepts. So let me write that down. If they are real roots, or you can also call those zeros, those will show up on your graph as x-intercepts. But if they are imaginary roots or zeros, those will not be x-intercepts. Okay, so whatever your degree is for your polynomial, that's the number of roots or zeros that your polynomial would have. So if it's a degree of 3, then you would have 3 zeros. And remember, the degree is just the highest exponent that you see on your variable. So we'll do some examples with this in a little bit, so don't worry too much yet. Just like I said, we'll do some examples. It just tells you the number of total zeros, Elizabeth. Yep, so they could be real or they could be imaginary. You don't know, but it tells you the total number of zeros that your polynomial would have. Good question. Alrighty, so if you expand that fundamental theorem of algebra, you can get what we call the linear factorization theorem, which is kind of just a fancy way of saying that we can factor these polynomials into linear factors. Linear means that each one of these factors just has an x in it, not like an x squared or something like that. And if you do that, then these numbers, these constants, constant 1, constant 2, constant 3, all the way to the last constant, would be your zeros. And those could be complex numbers. They could be real numbers or imaginary numbers in there. All right, so I'm going to show you some examples of this because I know this always looks a little bit more daunting than it actually is. So let's take a look at some examples before we panic too much. All right, so here's a first degree polynomial. So first degree just means that the highest exponent of x is 1. This is a linear polynomial. It has 1 0. Notice there's one factor here, x minus 5, and the 0 is just x equals 5. So be careful because notice that your 0 and your factor actually have opposite signs, and that's because if you set your factor equal to 0 and solve, when you cross that equal sign, your sign will change. So that's where we get that factor, get that 0 from the factor. So notice this is a positive 5, even though we had a minus sign in our factor. All right, so here's an example of a second degree polynomial. Second degree because that highest exponent is 2. So the fundamental theorem of algebra says we're going to have 2 roots. This particular polynomial factors, and it factors into x minus 4 times x minus 3. Okay, so just a quick review of factoring. The last sign, since it's positive, it tells us that we're going to have the same signs in the middle. They'll either both be positive or both be negative. And then when we multiply these guys out, we need to get a negative 7x. So that's why we have the negative 4x and then negative 3x. That gives us the negative 7. All right, so if I set each of those factors equal to 0 and solve, I get my 2 zeros of x equals 4 and x equals 3. And you can do the same thing for the third degree polynomial. This guy factors, which the factoring for this is a little bit trickier, so I wouldn't worry too much about doing the factoring at this point. It's just understanding that if it does factor into these linear factors, you can set each of these equal to 0 and solve. And so since there is a degree of 3, we have 1, 2, 3 factors. Set those each equal to 0 and solve, and we get 1, 2, 3 zeros. And that's what the fundamental theorem of algebra tells us. All right, and then the last example is a 4th degree polynomial. It's x to the 4th minus 16. Notice this is like the difference of squares. Remember, a squared minus b squared, if you factor that, you get a plus b, a minus b. And in this case, the first term that's squared is x squared. So we have x squared minus 4, x squared plus 4. X squared minus 4 factors again, that's also difference of squares, into x minus 2x plus 2. And this last one will also factor. Notice this time we have imaginary numbers as our factors into x minus 2i, x plus 2i. So we can get our 4 zeros there of 2, negative 2, 2i, and negative 2i. So if I were to look at the graph of this 4th degree polynomial, how many x-intercepts would this particular graph have? We have 4 roots. How many x-intercepts would I have for this last one? Very good. We'd only have 2 x-intercepts, even though there are 4 roots, and the reason is because 2 of our roots are imaginary. And notice that those have opposite signs, those 2 imaginary roots. We're going to talk about that a little bit more later. All right, so any questions in general about the fundamental theorem of algebra and how to find your zeros from factored form? Green checks if you are okay with this concept. Questions in the chat box if you have them. You can find the green checks above the names. So if you're good with the fundamental theorem and finding your zeros from factored form, give me a green check. If you're not sure, just go ahead and type your questions in the chat box. Seth, are you good with this? I think you are because you just answered that last question, but I just want to make sure. Awesome. Okay. Perfect. So now let's talk a little bit about Descartes' rule of signs. This is another one that looks a little bit trickier than it is when you read the explanation, but once we do a few examples, I think you will be good. So this just basically says if you have a polynomial that has real coefficients and you count the number of sign changes in the original function, so in, my pen just went away here. There it is. In the original f of x, the number of positive real zeros will be equal to that number of sign changes or less than that by an even integer. So if you count the number of sign changes in the original function, let's say you get 3 as your number of sign changes. You could have 3 real zeros, or if you subtract an even integer from that, like 2, you could have 1 real zero, positive real zero as well. Then to find your negative real zeros, you basically do the same thing, except you look at the sign changes in f of negative x. So again, we take the number of sign changes in f of negative x, and that number or that number less by an even integer would be the number of possible negative real zeros. All right, so let's take a look at an example with this, because I think looking at the example helps a little bit more than just talking through the words. All right, so we're going to use Descartes' rule of signs to determine the possible types of zeros for the function below. All right, so we have f of x given to us. So let's look at the number of sign changes in f of x. So if we go just from left to right, we have a positive term, a negative term, a positive term, and a negative term. All right, so we've got a sign change here. We have a sign change here, and we have a sign change here. So that gives us a total of 3 sign changes. So let's jot that down up here. F of x has 3 sign changes. So what that tells us is that we could have 3, or if we subtract an even integer from that, so subtract 2 from that, we could have 1 positive real root. All right, so that's the first piece of information. Now we're going to take a look at the second piece of information, which has to do with f of negative x. So let's find out what f of negative x is equal to. Okay, remember that just means we plug negative x in for all of my x's. So I have negative x raised to the 5th power plus 4 times negative x raised to the 4th power minus 3 times negative x squared plus negative x minus 6. All right, if I raise a negative number to an odd power, what type of answer will I get? Will it be positive or negative? If you raise a negative number to an odd power, do you get a positive or negative? Good, good, good. We get negative. So this is going to become negative x to the 5th, and now we can just stick that negative in front. When you raise a negative number to an even power, what type of answer do you get there? All right, perfect. So this second term is actually just going to stay positive 4x to the 4th. The next one is also to an even power, so this is going to stay as a minus 3x squared. It's not changing signs. The next one will be a negative x, and then our minus 6. So if I look at my signs, I've got a negative, a positive, a negative, negative, negative. So I have 1, 2 sign changes in f of negative x. Okay, so if you have 2 sign changes in f of negative x, that means you could have 2, or what's the other possibility for the number of negative real roots? 2 or what? Perfect, 0, yep, because you just subtract 2 every time. So 2 or 0, positive, oh, not positive, let's change that to negative, real roots. All right, so those are my possibilities, but that's not the whole story. Because remember that the fundamental theorem of algebra tells us that we have the same number of roots as we do the degree. So this is a 5th degree polynomial, which means that I should have 5 roots altogether. So let's see if we can write down our possibilities. We could have positive real roots. We could have negative real roots. Or I could have roots that are imaginary. All right, so let's look at these possibilities. I could have 3 or 1 positive real roots. I could have 2 or 0 negative real roots. So that means I could have 3 positive with 2 negative, or 3 positive with 0 negative, or I could have 1 positive with 2 negative, or 1 positive with 0 negative. All right, so if you put it in a chart like this, that'll help you determine the number of imaginary roots pretty easily, because altogether, what do these have to add up to? Do you remember how many we have to have altogether? How many roots? 5, exactly. So if we have this first possibility where we have 3 positive and 2 negative, how many imaginary do we have? Okay, 0, yep, because altogether this row has to equal 5 because 5 is our degree. All right, the next one, if we have 3 positive and 0 negative, how many imaginary must we have? Perfect, 2. All right, if we have 1 positive and 2 negative, how many imaginary must we have? Perfect, again, 2. 1 positive, 0 negative, how many imaginary? Awesome, 4. Excellent. So these are our possibilities for our number of roots from Descartes' rule of signs. All right, so green checks if you're okay with that example. Questions in the chat box if you have them. All right, perfect. Okay, so another thing we go over in this section is graphing by hand. I'm going to go through this example not super fast, but I won't spend too much time on it because this is not related to the actual assignment for tonight, but it is covered in this lesson. So to graph by hand, you want to kind of follow these steps. The first is to look at the degree, the number of zeros, and think about the end behavior. So I know this is a little tricky to read. This says f of x equals x to the third power plus 8x squared plus 19x plus 12, and it wants us to do it without the aid of a graphing utility. So that means no graphing calculator, no Desmos.com, just graph it by hand. All right, so what is the degree of this polynomial? That first term is x to the third. So what's the degree here? 3, very good. You can use a calculator for a lot of it. A graphing calculator would be helpful. You should be able to kind of think about how to do some of it without the graphing calculator, but you are allowed to use a calculator for most of it. All right, so if the degree is 3, how many zeros do we have? Okay, yep. Degree is 3, so we should have 3 zeros. Let's think about the end behavior. End behavior, remember, if you have an odd function with a positive leading coefficient, the left side will go down and the right side will go up. If you have an odd degree with a negative leading coefficient, the left side goes up and the right side goes down. If you have an even degree with a positive leading coefficient, both ends will go up. In an even degree with a negative leading coefficient, both ends will go down. So the odd ones go in different directions. I just kind of remember that because it's like always looks odd, I guess. So in this case, we have an odd degree because the degree is 3, and we have a positive leading coefficient. So we're looking at this first scenario. So you could say something like left side down, right side up. I mean, there's more mathematical ways to say that, but just to get an idea of what it's doing, that suffices. All right. Next thing we would want to do is find the y-intercept. So if you are a y-intercept, you're hitting somewhere on the y-axis. What is your x value if you are a y-intercept? If you're on the y-axis, what is your x value? It is a constant number, but what is the constant number that you are always equal to if you are on the y-axis for x? Yep, your x value equals 0. So we're going to set x to 0 and see what happens. So if I set x equal to 0, I get 0 plus 0 plus 0 plus 12. So my y-intercept then is equal to 12. Okay, so those parts are all pretty quick and painless to figure out. The x-intercepts are a little bit trickier. These are the zeros of your function. So we would need to solve x to the third plus 8x squared plus 19x plus 12, set it equal to 0, because if you're an x-intercept, your y value is equal to 0. So we would have to set the f of x equal to 0 and solve. So if you look at this, you'll notice that it's not easily factorable. So what we would do is list our possible rational zeros. Possible rational zeros, I think you did in an earlier section. Those are your p over q's. That's that rational root theorem. P are the factors of your constant term, which is 12. Q are the factors of your leading coefficient, which in this case is 1. So we kind of breathe a sigh of relief here because that means we're dividing by 1, so we don't have to do a whole lot of crazy stuff. So we just really need the factors of 12. So that would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And we could take all of those and divide them by plus or minus 1, but we're going to get the same exact numbers. So these at least gives us like a starting point to find our actual zeros for this function. These are our possible ones. So if we look at this original function, notice that it doesn't ever change signs in f of x. So that means there are no positive real roots. So automatically, you know, don't even bother plugging in a positive number because none of them are going to work. If you check f of negative x, you'll see that it has either 3 or 1 negative real roots. So what we can do at this point is use synthetic division or the factor theorem to find the zeros. I think synthetic division is probably the easiest one of those to use. So I'm going to start with like -1. Let's just try plugging that in. And again, this was done in a previous section, so I'm going to go through it kind of quickly, but if you need me to slow down, just type something in the chat box. So for synthetic division, you put the coefficients along the top, make sure you don't skip any. So we've got 1x to the third, 8x squared, 19x, plus 12. All right, and if this is a root, what should the number down here at the bottom right be equal to? It should be equal to 0. Okay, and I saw a question pop up that was really good. Do you just pick a random one, or is there a system? So there is not really a system. It is kind of just picking from this list. So I always, like, even though this is annoying to pick from this list, at least we have a list. So we know a possible place to start, and we do know, because f of x doesn't change signs, that none of the positive ones are going to work. So we know to start with a -1. Okay? All right, so I'm hoping that I get 0 down here at the end. So here's the process. You drop the first number, then you multiply. -1 times 1 is -1. And now you add. 8 plus -1 is 7. Multiply. -1 times 7 is -7. Add. 19 plus -7 is 12. Multiply. -1 times 12 is -12. And add, and we get 0, which is good. So that means that one of our roots, or zeros, I'll make a list up here, is equal to -1. So that's a real number. That means that it's an x-intercept. Okay, we could keep doing this with all of the other negative numbers, or another thing we can do is take a look at these bottom numbers. This gives us the coefficients of what we call the depressed polynomial, which is basically what we would get if we divided by the factor that goes along with x minus 1. So we lower our exponent by 1, so we have 1x squared plus 7x plus 12. Let's see if this factors. Because if we can factor quadratics, I think, pretty easily. If it factors, we're in good shape. We don't have to do any more synthetic division. All right, does this factor? Anyone remember how to factor? Yes? Yes, it factors, or yes, we remember how? I can, yep, just give me a second and I will do that. If you know how it factors, go ahead and show us in the chat box. Just type what you get. Okay, we get x plus 3, x plus 4. So let's talk about that a little bit. So the first term, and you can have those in either order. The first term is x squared, so to get that, we have x times x, no choice there. To get 12, we could use 1 and 12, 2 and 6, 3 and 4. We want to end up with a positive 7, so you can see that the only way we could do that is with the 3 and the 4, if they're both positive. And since we had to multiply to get a positive 12, they have to have the same sign. So both of these are plus. So it could be plus 4 and plus 3. And now, if you set each of those factors equal to 0, what do you get for those zeros from those factors? Perfect, -4 and -3. Awesome, so there are the 3 zeros, and because those are all real numbers, then those are going to be x-intercepts. So let me just show you how we would throw this onto a graph. So far we have the coordinates, -1, 0, -3, 0, -4, 0, and that y-intercept of 0, 12. -2, 2 I didn't plug in yet, but you could plug in a -2 and see what you get there. So basically what we would do is just plot all of these, and for the sake of time, I'm just going to kind of sketch this super fast. -1, 0, -2, 0. Oops, -2, 2 is what that was supposed to be. Let me delete that. Perfect. Got rid of too many things, as usual. -2, 2 can just be found by plugging in to the original function. -3, 0, -4, 0, and 0, 12, I'm just going to say is up here. I'm not counting that right now. And remember that our end behavior was something like this. So this function is going to do this kind of a little doohickey. And that should be going through there, but it's really hard to write with a mouse on the computer. So you get an idea of this really horrendous sketch of this graph. But at least we have some clue about what it looks like. If you want to get more precise, that's kind of what the rest of this is telling us. We can find relative extrema by looking in between our x-intercepts and finding these points up here, plugging those into the original function. But at least we have a pretty decent idea of what the graph looks like. Not so much like a pile of spaghetti like mine, but I'm trying to make it better, and I'm just making it 1,000 times worse. But anyway, we'll just go with it. All right, so are you guys okay with sketching by hand? I know that was kind of a quick overview, but green checks if you think you can do okay on that if you had to. Questions about any of that in the chat box? Okay, perfect. Thank you. You guys are kind for giving me green checks on that because that may have been the worst graph I've ever drawn in my life. Okay, so conjugate pairs. We saw earlier that with the imaginary numbers in that chart that we made for Descartes' rule of sign, that they always came in an even number, and that is because complex zeros, those are imaginary ones, always occur in what we call conjugate pairs. So that just means that if A plus BI is a 0, then automatically A minus BI, which is its conjugate, is also a 0. So for example, if 3 plus 2i is a 0, then so is 3 minus 2i. All right. Are we good with that? Any questions? Green checks if you're good with that. Questions if you have them. Okay, perfect. All right, and this is just more about the factoring business. So every polynomial can factor into linear and quadratic factors. So linear, remember, is like the x minus the constant. Quadratic factors would have something like x squared plus bx plus c. But if you have a quadratic factor, it can have no real zeros, which remember means that you would not be able to write it in this form. So if it has no real zeros, it can only have imaginary zeros if you still have the quadratic factor. So again, this theorem in particular I don't really find to be particularly useful. It's just kind of one of those, it's like, all right, thanks for that information that I can factor it like that. But it's not really going to help us out too much in the course of doing the problems. All right, so what we're going to do now is go ahead and knock out the assignment for 2.05b. So here's what you'll need to do. Follow along and complete the work on your own paper that we do. You will scan or take a clear digital picture of your work, and you will upload it to the assessment. Okay, so make sure that you show your work clearly as we go through everything, and make sure that you are participating in the discussion on the following slides. All right, so give me a green check if you are ready with paper and pencil, ready to rock and roll. Green checks when you're ready to go. Luca, are you with us? You have paper, pencil, ready to go? All right, maybe Luca will join us in the end or in a couple minutes. Okay, we're going to go ahead and move on. There you are. Okay, perfect. All right, so here's the description of the assignment. So it says in a word processing document, we're not going to worry about that. If you are doing a live session, you can just handwrite it. The questions are, how could you use Descartes' rule of signs and the fundamental theorem of algebra to predict the number of complex roots to a polynomial, as well as find the number of possible positive and negative real roots to a polynomial? Your response must include a summary of Descartes' rule and the fundamental theorem, and they must be in your own words, and you have to provide 2 examples. Each example has to predict the number of complex roots, so that means we need to know the number of total roots from the fundamental theorem, and we need to use Descartes' rule to tell the types of roots, and we have to explain how we found each of those predictions. And we're also going to provide a source for our information, and that about sums it up. So we're going to break this down in 2 pieces. The first thing that it says is to give a summary. So that's what we're going to do first. All right, so we need a summary of Descartes' rule and the fundamental theorem of algebra. Let's start with the fundamental theorem of algebra because I think that one is easier a little bit to talk about. So in the chat box, just give me a quick recap of your understanding of the fundamental theorem of algebra that we talked about earlier. Okay, I like it. It looks like you guys have a good understanding here. So let me try to type what I saw, kind of a summary. So the, oops, for some reason I'm not typing like I want to. The degree of the polynomial tells us the number of complex roots of the polynomial. All right, which I think is kind of what you guys were saying. Everybody said it a little bit differently, which everybody had a great interpretation. So any of those would be acceptable. Yep, and those imaginary ones would not be x-intercepts, but they would be considered roots. So they would still count for the fundamental theorem. And I should probably say that in the beginning if I'm being super fancy here or super correct. I should say the fundamental theorem of algebra states that the degree of the polynomial tells us the number of complex roots of the polynomial. All right, so that is that one. Now for the one that's a little bit harder to kind of put into words. Oh, complex roots, that's a good question. Kind of think about the complex number system. So the complex number system has 2 pieces to it. It has real numbers, and it has imaginary numbers. Samantha, you can do either one, your summary or the one that I'm writing, as long as it's pretty close to what I wrote. That's totally fine. Either one is acceptable. Yeah, as long as you don't say something like the fundamental theorem says bananas are fruit or something like that. Like you have to pretty much say what we just said. But all of the summaries I read were good, so I think we're good. All right. Awesome. So now let's talk about Descartes' rule of signs. So this one's a little bit trickier. Descartes' rule of signs says the following. All right. So let's first talk about the sign changes in f of x. What do the sign changes in f of x tell us? Okay, the number of positive zeros. What type, when we say positive, we can be a little bit more specific. Okay, real zeros, good. The number of positive real zeros. Oh yay, Samantha, you got the first little emoji thing there. When you put an X in parentheses, it like pops up as a little girl. Okay, which always makes me laugh. No, it's funny. I love when it happens because we'll see lots of random ones throughout the year. Okay, so the sign changes in f of x tell us the number of positive real roots, or what should we do with that number? Because we can't just leave it. Like if we get 3, it's not only 3. It could be 3 or what? Or 1. Okay, so we have to subtract. Yep, or a number less than that that is even. So let's see how I can say that, because I always just think just keep subtracting 2, but it's kind of hard to put it into words. So tell us the number of positive real roots, or that number less an even number. Okay, I think that works. And now we can look at the sign changes in f of negative x. So I think this is just basically the same thing, except we're going to swap out the word positive for what word? Okay, yep, negative. So I was like, where did you guys go? Okay, so the sign changes in f of negative x tell us the number of negative real roots, or that number less an even number. All right. So there we have our summaries. All right, so now we're ready to do our examples. So give me a green check when you're ready to move on. All right, awesome. Okay, so now we have to give 2 examples. So we'll just start with our first example. We're going to give the example and predict the number of complex roots for each. And we're going to explain how we found the number of complex roots as we go through it. So we're going to start off with f of x. Okay, and I would like a number, let's do a number 5 or less. Just type a number 5 or less into the chat box. I'll see the first one that comes up. 3. Okay, so we're going to do a polynomial with 3rd degree. And then we'll have a constant. All right. Luca, give me a number. It could be any number, positive or negative. Luca, type in a number, any number, positive or negative, whatever you want. 2. Okay. Samantha, give me another number, positive or negative. Okay, minus 4x squared. Elizabeth, positive or negative number? Okay, negative 21. And Anna, positive or negative number? Okay, 3. All right, perfect. So here's our polynomial that we're going to use. All right, so what is the degree of this polynomial? 3, perfect. So according to the fundamental theorem of algebra, we have to explain all of our steps here. So I'm going to do that over to the side. How many real, or not real, how many complex roots should I have? I think you guys typed it. Yep, 3 complex roots because the degree of the polynomial is 3. Okay. Now we're going to do Descartes' rule of signs. All right, so first let's look at the sign changes in f of x. So f of x has, let's count the sign changes. You guys count them, I'll count them, and we'll see if we agree. All right, perfect. Has 2 sign changes. So we can have how many positive real roots? If we have 2 sign changes in f of x, how many positive real roots can we have? Perfect. You guys are awesome. 2 or 0. Okay. Let's talk now about f of negative x. All right, so remember when we plug in the negative x, only the ones that have an odd degree are going to change signs, because the even degrees, it'll stay the same sign. So f of negative x will be negative 2x to the third minus 4x squared plus 21x plus 3. All right, so how many sign changes do we have in f of negative x? Yep. So f of negative x has 1 sign change. So we can have one negative real root. Okay, and another thing that's helpful to do is to think about kind of the different combinations that are possible. We've got positive real roots, negative real roots, or if it's not real, it would be imaginary. So we could have 2 or 0 positive, and we can only have 1 negative. So that's going to kind of limit our possibilities here. And according to the fundamental theorem of algebra, I have to have 3 zeros altogether. So if it's this first option, 2 positive and 1 negative, how many imaginary would I have? Perfect. All right. The second option, if I have 0 positive and 1 negative, how many imaginary would I have there? 2. Perfect. And notice that's an even number, which is good because those come in conjugate pairs. All right, so that's it for our first example. Green checks when you're good with that one. Questions in the chat box if you have them. All right, awesome. Let's do another example. All right, so we have to make up another polynomial. F of x equals, all right, let me have a number not 3 that's 5 or less. 5, okay. All right, so we're going to have x to the 5th, x to the 4th, x to the 3rd, x squared, x, and then our constant. All right, so Elizabeth, a positive or negative number, please. Negative 12. Anna, a positive or negative number, please. 7. Lauren, a positive or negative number, please. 3, okay. And Luca, a positive or negative number, please. 8, okay. And Samantha, a positive or negative number? 20, okay. And Seth, a positive or negative number? 6. All right, awesome. All right, so let's talk about the fundamental theorem of algebra. So how many complex roots will this polynomial have? All right, I see a couple of conflicting answers. I've got 6 and 5. What do we think? 5, okay. How do we know it's 5? What tells us that it's 5? Yes, exactly, because the degree of the polynomial is 5. Okay, perfect. All right, now let's do a little bit of work with Descartes' rule of signs. So let's look at f of x and count the number of sign changes. So f of x has how many sign changes here? How many sign changes do we have in f of x? There's the one. Okay, so we just have one sign change in that first term. So f of x has one sign change. So we have how many positive real roots? Perfect, just one. All right, let's take a look at f of negative x. All right, remember, only things with odd degrees are changing signs. Everything else will stay the same. So this is going to become positive 12x to the 5th plus 7x to the 4th minus 3x to the 3rd plus 8x squared minus 20x plus 6. All right, so f of negative x has how many sign changes? All right, perfect. Seth, it has 4 sign changes. So we can have, what do you think? If there's 4 sign changes, how many negative real roots can we have? Yep, perfect. We could have 4, subtract 2, we get 2, subtract 2 again, we get 0. So we can have 4, 2, or 0 negative real roots. All right, so let's see a chart of all of this, of all of our possibilities. All right, we know that no matter what, we have only one positive, but we could have 4 negative. We could have 1 positive and 2 negative, or 1 positive and 0 negative. All right, so let's look at our imaginary ones. If you have 1 positive and 4 negative, how many imaginary would you have? 0, very good. If you have 1 positive and 2 negative, how many imaginary would you have? 2, very good, because it has to add up to 5. If you have 1 positive and 0 negative, how many imaginary would you have there? 4, perfect. Great job, guys. All right, awesome. So green checks if you're good with this one. Questions in the chat box if you have them. number. So then the last part was just to list the sources for your information. So where did we get our information tonight? Let's say the live lesson maybe. Hopefully the live lesson taught you something. And the live lesson notes came from the FLVS course material. And maybe I taught you something too, I don't know. That works. So we didn't look up anything extra. If you looked up other stuff on the internet about Descartes' rule or fundamental theorem, then you would obviously put that here. But tonight we just went with what I presented in the lesson. All right, so how do you submit, scan, or take a clear digital picture of your work? Make sure that you type in the student comment section that you attended the live lesson on September 12th, or that you watched a recording of the live lesson, because that will protect you from getting an academic integrity violation. Obviously, many of you are turning in the same work. So you can just upload your clear digital picture or scan to the 2.05B assignment, and you are all set. All right, so let me go ahead and stop the recording.